Okay, today's class we'll discuss with module 3 about a Poisson's and Laplace equation and also about the Uniqueness theorem. Before we go with the module starting, we just go with a small quote who told the John Newburn about people can be divided into three groups. Here, those who make things to happen, and those who watch things to happen, and those who wonder what happened. In these three groups, which where you want to place, you decide now only, because still you are making your engineering career. So I hope with my students will go with the first one in this group. Okay, this is a small quote, and in your when you referring Sadiku textbook, you will be getting rather than the information about what is the EMFT subject, you will be getting some of the quotes which are very innovative, instead of it motivate you. Quotes will be there. You can refer of those also. Somewhat other than reading of the EMFT, you can go through that. Okay, now we will start with our topic about why we have to go with the Poisson's and Laplace equation. Is there any necessary? Yes, it is a necessary thing. Where in the first module, what we learned about the Coulomb's law, or else Gauss law, what all things about electromagnetic field intensity, what it is giving the information for us for a one charge where it is placed, it may be a positive charge or it may be a negative charge. For these charges, what is the force in between that, and what is the intensity it can offer for us. We studied of those things only, but we taken a surface integral. Yes, for any of the surface, any 2 point charges, how it is going to be reacting, what is the force, what is the electric field intensity, how it is going to be. We learned of those things only, but is there any limitation for that? How much we have to take? Is there anything we don't that to get what is the boundary conditions, so that we can go with our intensity or else the potential V is that information will be given by the Poisson's and Laplace equation. How the problems are going to be solved, that is about the uniqueness theorem. The same thing here it is given. uh, the Coulomb's law and Gauss law, when the charge distribution is known as E is going to be minus del of V, when potential is known throughout the region. But what is the limitation, what is the boundary we have to take, we don't know that. That's what practical electrostatics problem, where only electrostatic conditions about a charge and potential at some boundaries are known, and it is desired to find the E and V throughout the region. Such problems are going to be tackled by using of a Poisson's or Laplace equation, or a method images that they are usually referred to as a boundary value problems. To get that boundary value problems, we'll be using by using of the Poisson's and Laplace equation. Next, we'll go with the what is the Poisson's equation. This all in terms of going to be any theory here. What are the equations they proposed? From that we will be learning how a field intensity we can, or else a potential we can derive, or else the equation what we will be going to give, and what is the solution for those things. In this case, the Poisson's and Laplace equation, this is important topic. Poisson's and Laplace equations are derived from the Gauss law for linear and isotropic material medium. That is, these equations are we already taken. Again, considering of those equation, del dot D is going to be equals to del dot epsilon into E, flux density, electric field flux density, and the magnetic electric field intensity, that is equals to rho V of that area, how much it's going to be considering, and E is going to be equals to minus del into V. Then substituting the equation 2 in equation 1, 6.1 here it is referred. Then what we will be getting Instead of E, I can substitute here as del dot minus epsilon del into V, that is going to be equals to rho V. Then for an inhomogeneous medium, then equation is going to be del cross equation 6.3. This equation is going to be del cross V is going to be, just solving here, del into del cross del square into V, that is going to be equals to minus rho V divided by epsilon. What the equation we got, that is of that surface area to the where it is placed, that is epsilon is giving the information which material we placed in either in a free space or in a some of the conductive medium. What is the value of that? This equation del square V is equals to minus rho V divided by epsilon is known as the Poisson's equation. You have to remember this equation. That is about the Poisson's equation. The special case for this equation occurs when rho V is going to be equals to 0. When rho V is equal to 0, it means what? For the charge in the free region where it is not bounded with any of the medium. Then equation is going to be del square V is going to be equals to 0. Then that equation is nothing but a Laplace equation. Observe here, del square is going to be equals to minus rho V by epsilon. This is the Poisson's equation. When rho V is going to be equals to 0, what the equation will be getting, that is del square into V, that is going to be equals to 0. This equation is nothing but our Laplace equation. Noting in taking, that is epsilon out of the left hand side of the equation 3, this part, assuming that the epsilon is a constant throughout the region in which V is defined. Epsilon is taken in a constant, and where the potential, what it is going to be changing, that we have to define. For an inhomogeneous region, then epsilon is not a constant. In this case, in the equation 6.4, does not follow the equation 3. When it is coming, when it is not in place, it is not going to be considered. Then equation 6.3 is a Poisson's equation for inhomogeneous medium when rho V is going to be equals to 0. What the equation we taken? This is what the equation we taken here. It is for homogeneous medium. In this 6.3, what the equation it is getting, it is for the inhomogeneous equation, and when rho V is going to be 0, then you will be getting the Laplace equation for the inhomogeneous medium. Then Laplacian operator, that is del square, is considered in the previous cases. Those things they are telling. The Laplace equation in the Cartesian, cylindrical, and also about the spherical coordinate systems are taken as dou square V divided by dou x square plus dou square dou y square plus dou square V by dou z square, that is going to be equals to 0. This is in the Cartesian. Next, in terms of cylindrical, 1 by rho dou divided by dou rho into rho dou V divided by dou rho plus 1 by rho square dou square V divided by dou pi square plus dou V dou square V divided by dou z square, that is going to be equals to 0. This almost the equations are similar to the curl equation what we taken. Then about a spherical coordinate system, 1 by r square dou by dou rho dou r square dou V by dou r, then plus 1 by r square sine theta dou by dou theta of sine theta dou V by dou theta plus 1 by r square sine square dou square V divided by dou pi square, that is also going to be equals to 0. These are all the basic equation about a Laplace equation for Cartesian, cylindrical, and also for spherical coordinate system. Then depending on the coordinating variables used in the to express the V, that is V of xyz, rho pi z, and rho V r theta pi, the Poisson's equation In those coordinate system, Poisson's equation can be obtained by simply replacing 0 on the right hand side of equations, all three with minus rho by f long. This was the Poisson's equation. Next, Laplace equation is of the primary importance in solving the electrostatics problems involving a set of conductors maintained at a different potentials, where the some of the conducting medium where in which were values of V voltage it will be differing for those in the more problem. Some examples here given, including capacitor and vacuum tube diodes. In such applications, we'll be using of our Laplace equation. And Laplace and Poisson's equations are not only useful in solving the electrostatic problems, but also they are used in various other field problems. Like some examples here given as voltage would be interpreted as magnetic potential in magnetostatics. Magnetostatics as temperature in heat condition in the function in the fluid flow and head in a speech. To do with this, in such applications will be using this about Laplace and Poisson's equation. Rho divided by f long. Then the square root is 0. The name only is giving. When we are telling some person some methods are unique, why the term is going to be taken as unique? Can anyone tell? A simple question. Yes, Latashri. Vamshi. Okay, we'll proceed now. The uniqueness theorem. Uh, Here, the method what we'll be going for equations, what we'll be going for a plus b whole. The problem it is given in terms of that a square plus 2ab plus b. It was whatever the equation it is in terms of supply formula. That is like here also what we are the Uniqueness theorem is telling us, Laplace equation is the one where it is giving the solution for whatever the boundary condition I am going to be considering for my charge distribution and as a potential distribution of a Gauss law, what we learned in the previous cases. For them, how it's going telling they're asking of the proof. What we taken? What is the equation is going to be? How it is going to be when we are going to consider of Gauss law or any of the laws. What we are going to be is that Poisson in a unique fashion. For that reason, a Laplace equation is telling as a unique. If we go with the signal system or any of the higher learning of those things in higher semesters, we'll be using the Laplace transform. In this case, Laplace equation. In a general case, I'm telling, we'll be using of the Laplace transforms, Laplace equations. Those will be giving a more accurate values, and about the stability we can find out easily of any of the system what we are going to learning in our engineering field or else in the basic fields where we are going to be, right? The same thing here, statistical way we can go with a graphical way, or else a numerical or experimental ways. There are different methods we can propose of solving any of solving the Laplace equation in different ways gives a different solution. If I am solving for one analytical way, if I apply Laplace, if I go with some other method, again I will make you the get the different. Therefore, before we begin to solve the Laplace equation, we should answer this question. They are telling, just I'm telling the same thing here for you all. If a solution of a Laplace equation is satisfies, observe here, if a solution of a Laplace equation satisfies a given set of boundary conditions, some boundary conditions given in terms of integration, boundary condition in your mind, if it is telling means you should imagine about your integration. What is the boundary condition? What is the limit it's going to be? Boundary condition. Is there any possible solution for us? The answer is going to be yes. Whereas there is only one solution we will be getting, not a difference for different methods, different solutions will not get. For one method, you can, if you proceed with that method, you will be getting an exact solution for that. The solution is we say that the solution is going to be a unique. Thus, any solution of Laplace equation that satisfies the same boundary condition, that is important, must be the only solution regardless of the methods used. For that reason, this is known as the uniqueness theorem, and theorem applies to any solutions of Poisson's or Laplace equation in a given region or else any of the closed surface. That is about the uniqueness theorem. Next, we'll go with exactly what it is going to be, how we have to proceed to solve any of the equation if it is given by using of the uniqueness theorem. The theorem is proved by contradiction. We assume that there are two solutions for V1 and V2 of Laplace equations, both of which satisfy the prescribed boundary condition. Both will be satisfying the boundary conditions. Then del square V1 is going to be equals to 0. Then del square V2 is going to be equals to 0. These two solutions we got. Then if it is having both are 0 means, then of course directly we can tell that V1 is going to be equals to V2 on that boundary. Then we considering their differences, what is going to be? Vd is going to be equals to V2 minus V1. Then del square of Vd is going to be what? Del square V2 minus del square V1, that is also going to be equals to 0. Here it is taken as 0. For that reason, 0 only. Then Vd is also going, the difference between the two potentials is also going to be 0 on the boundary. Then according to equation 6.9, this from the divergence theorem. Again, we will be using of divergence theorem. That is about integration of V of that particular volume. That is del dot A is going of dV is going to be equals to a closed surface of that vector, that is A dot ds of that surface, where S is the surface surrounding the volume V and is the boundary of the regional problem. Then we let here in this case, instead of A, I can substitute here as VD dot VD and use the vector identity, that is here the formula, that is del dot A is going to be equals to del dot VD del VD, that's going to be VD del square VD plus del VD dot del VD. But del square VD is what? It's going to be 0 only. Therefore, del A is going to be equals to, the remaining part will be this much, del VD dot del VD. Then substituting this equation here, therefore, then we will be getting as integration of with volume del VD dot del VD into dV is going to be equals to, in terms of volume, in terms of surface, closed surface integral VD dot VD del VD dot ds. From equation 6.9 what we taken, then 6.11, these two equations, is evident that right hand side of equation 4, you observe here, it's going to be vanishing by itself, because the what's of value we got, VD is also 0, everything is 0. Then if I substitute in the equation, again I will be getting the 0 only. For that reason, the equation is going to be, hence the equation is going to be integration with the volume of mod del VD whole square into dV is also going to be equals to 0. Since the integrated is everywhere, it is of a positive value, then del VD is going to be equals to 0. Yes, integration will be going for. Then, or you can tell that VD is going to be V2 minus V1 is going to be equals to constant everywhere in the volume. Means in the volume, the whole volume, if I am going to be considering the potential, what it is be flowing, the supply will be giving, yes, positive negative will be giving, what's the voltage will be flowing in this system, right, in this whole system, it will be same. Is there any difference is going to be? The components of resistor, capacitor, if you are using it, based on that, it may take any different values. But if I am going to be using of a copper wire, right, if I am giving a supply for this, if I am giving 5 volt supply, that 5 volts only it will flow in this medium, as in a copper wire, right, any of the medium which you go in for. That's what the meaning here giving the information for us. The meaning is same. The VD, the difference, what it's going to be in any of the medium, in a volume or anything in medium, just if it will be easy to remember. For that reason, if I'm going to be passing through a copper or any of the wire, right, the same will be flowing in that. Is there any difference? Here it will be flowing of any through 2 volts, or here it's going to be 3 volts? No, 5 volts it will be flowing with the 5 volts only. That's what here telling, that VD is going to be equals to V2, the potential difference what's going to be constant everywhere in that volume, any of the system, if we'll be using of that. Then what next condition is going to be? But equation, these two equation, that is 6.15, must be consist with equation 6.9. This has to be considered. Hence, VD is going to be equals to 0, or else V1 is going to be equals to V2 everywhere in the medium. Then showing that V1 and V2 cannot be different solution for the same problem. That's what the conclusion what we will be giving from the small derivation. Then what is this uniqueness theorem is telling us? What is the exact definition is of the uniqueness theorem? If a solution to Laplace equation can be found that satisfy the boundary condition, Laplace equation can be found, we find that satisfies the boundary condition, then that the solution is of the unique one. First you have to do, we have to apply the Laplace equation, we have to come with the satisfying the boundary condition, then the solution what we will be getting, that solution is of a unique one. That's what a uniqueness theorem. Then what are the steps we will be going for to apply the uniqueness theorem? Here it is similar steps can be taken to show that the theorem applies to the Poisson's equation, and to prove that the theorem for the case where electric field or potential gradient is specified on the boundary. How it is going to be? Some steps are there. Before we begin to solve the boundary value problems, the three things when we are going to be taking of this, we have to keep in mind uniquely. That is, the first one is the appropriate differential equation. What you will be taking, that should be correct for Laplace or else for the Poissons. Then the solution for the region, in which region you are going to be applying. Then the prescribed boundary condition. What's the boundary condition will be considering. These three you should be considered when we go with the solving the problem. Next, what they are telling, a problem does not have a unique solution. A problem does not have unique solution and cannot be solved completely. In such cases, if any of the three item is missing. In these cases, if it is not giving a solution, means in these three cases what we taken, either it may have a solution for the region or boundary condition is not proper, or else which equation you've taken, it will not be a proper one. That's what the mistake will be there, or else a missing item will be there. That's what they are telling for us. This is about a uniqueness theorem. Again, next class we will solve the problems based on a uniqueness theorem. How to apply the uniqueness theorem for a given problem. Different conditions, what those can taken. We will consider of those in the next class only.